So we're going to take a closer look at this problem number 9 in the sample set of the PARCC exam. And apologize for my sick voice, but can't be helped. A scientist is studying the cooling patterns of a particular material over time. Her research requires heating a sample of a material to 200 degrees Celsius. She records the temperature of the sample as it cooled to 0 degrees. The table shows the data collected during the first 2 minutes of the cooling process. And for those people who did connected math, this is exactly the same problem as an investigation you did with cooling hot chocolate. So if that helps you remember about this problem, great. And it was in a book called Growing, 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 which obviously, since I'm saying it, and if you remember it, that covers what kind of relationships? Growing, growing, growing.
Linear or exponential?
Exponential relationships. So we know pretty much what's going to happen by recalling our past investigation. So we have our table here, and then we have a nice graph, and we have samples A, B, and C. And it says the figure shows a scientist's data. Data points are plotted on large dots. 3 possible models for the data are shown. A linear line of best fit, that's our blue line. We know it's linear because it is a straight line. Then we have a quadratic model. Now a quadratic model is going to be a parabola, and you know a parabola is, in this case, if it opens up, is going to be going down for a while and then traveling up. So our quadratic model is A, because we've hit our vertex right about here, and we're traveling back up the parabola. And we also have an exponential model, which obviously is B. So the question A is asking us which model is linear, which one is quadratic, and which one is exponential, which model is the best for the amount of time that we see, and explain why the other models do not fit the data well. Well, I'm not going to type it out. I'm going to explain it. A is obviously quadratic because it is starting to head up, which means in the context of cooling liquid, that our liquid, while it was sitting out, would spontaneously start to heat up again. And you know that makes absolutely no sense. So I don't think the parabola is going to make any sense whatsoever because it's starting to get warmer right about here. No, no, no. The linear model is the line of best fit. And if I continue this data, you'll notice that I'm going way below 0. Is that going to make sense? If I put a cup of hot chocolate on my desk, is it going to get to be below 0? Probably not. So the linear model really makes no sense either, which leaves me with the exponential model, in which case is going to make a lot of sense, because if my room temperature is 0, as I continue, it's going to continue getting closer and closer and closer to 0 until it actually hits 0. So obviously the exponential model, model B, is going to be the model that is the best for this problem. Moving on. Hello, Mrs. Yema.
Is it weird that he sits here and talks to himself?
You know, it's a good thing I have this microphone because otherwise people would think I'm crazy.
Otherwise?
Otherwise.
People would think you're crazy.
I think they're crazy. I think they question my sanity anyways.
People think you're crazy.
All right. But this would be a good time for Yema to use some Yema-isms.
Right. I don't know what you're talking about.
All right. Construct a function using the type of model you described is the best fit. So we need to have a exponential model. And so when it says model, you have 3 options. You can make a graph. We already have a graph. You can make a table, but we already have a table. So really, we're stuck making an equation. So an exponential equation, you'll remember, is going to be written in the form y is equal to a times b to the x power. But since they want function notation, we're going to have f of x is equal to a times b to the x power, where a is the y intercept, and B is the growth factor, or in this case, since we're getting colder, it's going to be a decay factor. So I know that I started at 200 degrees Celsius, so I know already that my y-intercept is 200, so I have f of x is equal to 200 times my b value. So what am I dividing every time? So I need to go back to my table. It may actually scroll up at some point. There we go. All right, and I'm going to use my calculator here because I have a calculator icon up here. Maybe I should use the one. Yeah, let's see if it'll work while I record. All right, look at that. So the question becomes, what did I multiply 200 by to get 141? Well, for me to figure that out, I have to work backwards. 141, that's 140. 141, let's try it at the third time's the term. 141 divided by 200. That's 2,000. Because this is going to give me a bogus answer. So let's try this again. 141 divided by 200. So that's 0.705. Well, let's see if that happens again. So this time I'm going to use this number and this number. So 101 divided by 141. 0.71, 0.72. And then for my last one, and I'm going to have to find a number that makes sense here, divided by 101 equals. So I'm all sort of in the same basic range. But then the problem becomes, I don't have a rate of 1 up here, do I? All right, so what I would do, the way I would get around this would be, there's part B. So what I would then do is, I would say that my decay factor, in this case, is going to be about 0.7, or maybe 0.71 to the x, where I'm going to say x is equal to groups of 20 seconds. So that way, I don't have to worry about how much it cools down every second. I can just worry about my groups of 20 seconds, which is what I had in my table. So I made sure that I used function notation with my f of x instead of using y. I defined what my x value is equal to, and I should probably also say that f of x is equal to temp. And I think I've successfully answered all of the parts.